it's fine. Good. All right. Good evening, everybody. I'm going to talk a bit about the pre-stabilized laser for advanced LIGO. So this is a more special topic, and it's also a bit more technical topic than what we learned so far. But I'm going to try to also make it a bit broad and tell you a bit of the tricks, how to develop this laser and the tricks we used. But today I just want to give you a broad overview on that laser system. And I want to start with some of the requirements for the advanced LIGO laser, because that's kind of the baseline where we started to build that thing. I'm going to show you the main laser concept then we used, the different components we were using. And then I think that I have to talk a bit about on how we fulfilled some of the requirements. And today I'm mainly going to talk about the mode selection in high power lasers in general, but also in this case, in this special case. And that will conclude the transverse mode selection and also the longitudinal mode selection. So I'm going to start with the requirements. And I think we already went through most of the points that are on this slide. So we already learned that big masses in space, like rotating black holes or rotating neutron star systems, create gravitational waves. And we also already learned that the amplitude of these gravitational waves is rather weak. So Peter pointed out that the strain which we expect might be in the order of 10 to the minus 21. And in this regard, it helps to have have these large instruments for the detection. Here is a picture of LIGO Hanford with these 4-kilometer arms. And we also already talked about the basic principle. So we have a laser here, and we send the light from the laser to a beam splitter. Then it's split and sent to these two end test masses. It's sent back. And then we get an interference pattern, and we can align the arm lengths such that the electric fields of the light traveling in one arm and back in the other arm interfere in a way that these hills and valleys here overlap, such that if we sum that up, here we get a destructive interference, so we basically get a dark output port. And we just heard that if a gravitational wave, like this one, for example, in one polarization, in this case it might be plus polarization, hits the arms, then these arms are stretched or compressed, and that causes that these traces here are shifted in some way, and so it's not like a hill and a valley overlap, but it might be that they are a bit detuned, so the phase is no longer 0, but some other value, and that gives you some signal at the output port here. So, and I'm not going to comment any more on this. I think we already learned everything we need to know. But I'm going to talk about this laser. And the task if we want to build this laser is that we have to build something which can be effectively coupled into these cavities. And we also already heard that there are some issues with noise, so we have to build something which is as less noisy as we can possibly build that thing. So that's going to be the challenging part. And here are some requirements which I basically took from a document that LIGO came up with. So that was kind of the baseline on how we designed the laser. One is that for advanced LIGO, we want to have an output power of that laser of 180 watts. So before that, in enhanced LIGO, it was 35 watts. And it's like some more output power helps in terms of short noise up to a certain, from a certain frequency on, like 100 hertz or 200 hertz, I think, or so. And in that frequency regime, the signal to noise ratio goes with 1 over the square root of the power. So if we would have more power sending through that instrument, that would help in terms of noise. We also want to have a single transverse mode operation. So we want to have a TM00 beam, a nice round beam with a Gaussian intensity profile. And this kind of profile has a peak intensity somewhere in the middle, and then it rolls off on the sides. And it also, especially in the focus, has a plane wavefront, and that helps in terms of the interference contrast, because it's basically what one wants. The laser has to create a linearly polarized output. That is always handy to have if one works with laser, because linearly polarized light can be easily blocked. So in terms of back reflected light, it's kind of not too hard to put a Faraday isolator there and then get rid of the back reflected light. But there are also some issues with coatings on mirrors, like that the reflectivity is different for S and P polarization, so for the two polarization directions. And that's something one don't want to have. So if one would have unpolarized light, then one would have different components, so different reflectivities for the polarization components, and that would make things really complicated. And then there are some issues with the frequency stability, which I'm going to comment on these numbers later. I'm going to give a lecture on stabilization of the PSL, and I want to comment on that. But I think one can really imagine that, for example, if the amplitude is not stable, so if the power fluctuates of the laser, then that would couple into the signal that people want to try to measure. So that would be not a good thing if we couldn't build a low noise laser. And of course, then there are some technical issues, like that system should be highly reliable. So we want to have a system which basically runs night and day, 24 hours a day, 7 days a week, and so on. So that's not allowed to fail. And if it fails, then it should at least be easy to maintain. So it can't be too hard to fix problems which might occur with that system. Okay, now I'm going to show you an overview of the laser concept. And I have this picture here, which should give you an idea. So the whole thing starts here with a seed laser. That's an NPRO. And I'm going to show you on the next slide actually what that exactly is. And this laser actually has all the properties one wants for this interferometer. It's low noise, it's single frequency, has a nice round beam profile. So everything one wants except the power. The power is only 2 watts for that thing, so that needs to be amplified. And that's actually what this MOPA, the master oscillator power amplifier does. So this is a master oscillator, and then the light is directed through various components here, through this box. And that's a power amplifier, so it's directed through some crystals, which are pumped from this side. And it's built in a way such that the good properties of this NPRO haven't changed, but the output power is 35 watts, which is coming out here. And that's actually what we call the front end that has been used for the previous version of LIGO, enhanced LIGO. And yeah, it's still in use as a front end. But for advanced LIGO, it's further amplified by this high power oscillator. And I'm going to show you how that works in a couple of slides. But the light is basically going through 4 neodymium yak crystals. So here is a mirror, and then it goes in this path through that thing, and then it comes out here. It's then filtered by a high power Primo cleaner, and I'm not going to talk today about it. I'm going to talk about in another session on what that thing does. And then there's also some diagnostics, which I'm going to talk about tomorrow. So today, this part is a topic, and I'm going to start with the seed laser here, this NPRO. NPRO stands for non-planar ring oscillator, and it's actually a monolithic ring laser. As you can see here, it's not really big. It has about the size of my thumbnail, maybe, if one excludes all the electronics and so on around it. And it's monolithic. That means that the laser crystal itself is the whole thing, but there are no mirrors around. So normally, if you want to build a laser, you need some active material and then some mirrors around, and then the light is bouncing around it. But in this case, the mirrors are directly coating on the surfaces of that thing here. And that makes it really stable, because you don't have any mirror mounts which can wiggle around or so. And that's one of the key points why this thing is extra stable. So as I said, it's a ring laser, and then the question might raise, okay, if it's a ring laser and the light is going that way, why doesn't it go the other way around, and then you get two output beams? And the trick to do that is this non-planar part. So this end phase here is coated in a way such that that it's good for a linear polarized light. And so the light traveling around here is linear polarized. But if you bring it out of that plane, then this polarization is slightly tuned. So it's a bit tilted. And that's also true for the light traveling in the other direction, theoretically. But if you now apply a magnetic field to that thing, so that's what this H is here, then you have a certain Faraday constant, so you get a Faraday effect. And that actually rotates for one direction here. The strength of this magnetic field is picked such that that this rotation, which is caused by this non-planar thing, is just rotated back. For the other direction, it adds up. So you make this tilt a bit stronger. And because this surface here is coated for a certain polarization, one of these directions see high losses, so that's not really amplified. So the other direction is the one which gets all the gain. So that's why this thing is unidirectional. Okay, so I already said that that's a neodymium crystal here, so it emits light at 1064 nanometers. There's a single transverse mode, so this nice round beam profile, which is ensured by a certain pump configuration. So the pump light is sent in from this surface here. It's a single frequency laser. So what means single frequency? In the case of an N-Pro, it has a line width of about 1 kilohertz. And that's ensured by the length of this round trip here. So as I said, it's a rather small crystal. And the separation of the longitudinal of the modes is basically given by C over L for a ring resonator, C over 2L for a standing wave cavity. So if L is small, then you have a big separation, and so only one mode fits into the gain spectrum of that crystal here. So the output power is linearly polarized, and as I already said, the output power is 2 watts, which is already a lot, but not a lot for the gravitational wave detector. So we have to amplify that in this master oscillator power amplifier. And that's a 4-stage neodymium vanadate amplifier in this case. Vanadate has the advantage that it has a good absorption, so it's kind of easy to build an amplifier from that. So that's why this material is picked. And the wavelength where light is emitted is also 1064, so that's perfect for this purpose. So the light from the N-Pro is cleared up a bit in the polarization. So what's coming out here is slightly elliptically. So the polarization ratio is something like 5:1 or so, but that can be easily cleaned with a wave plate set here. It's sent through an isolator, which actually acts as an optical diode, so no light is going back to the N-Pro. And then it's sent through 4 of these neodymium vanadate crystals, and they are longitudinally pumped. So the pump light has to be separated from the laser light here. So this is 808 nanometers, this is 1064. And there are easily dichroic mirrors available which do that job. So they are transparent for 808 nanometers and highly reflective for the laser wavelength. And yeah, then the light is just sent through these crystals. And if one does everything right, so if one picks a right pump spot size here coming from these laser diodes, and if one does a proper mode matching, because one expects some thermal effects in these crystals, one has to compensate that by a certain lens, then the properties of the output beam here are about the same as for the N-Pro beam, except that one adds some technical noise. But it's still a nice round beam profile, and one gets an output power of about 35 watts. So here's a picture of that thing. The crystals are here in this gold-coated clamps. The pump light is coming from this side here, and it's fiber coupled, so the actual pump light source is somewhere outside the box. And yeah, that's a nice little device. So as I said, that has been used as a front end for the eLIGO stage, so the former stage of LIGO. It comes in this nice box with all these connections and a user interface, some software and so on. And it was quite successful. Actually, it was so successful that the people who built that thing founded a spin-off company from the Laser Zentrum, where this laser development was going on. So that's called Neolaze. And they actually still making these lasers also for other purposes. They do some frequency doubling. They amplify some pulse lasers even and so on. So one can actually order what one wants. Here's an output power curve of that thing. So this is the seed power, so the power coming from that NPRO sent through that four stage system here. And as you can see here, if you have not too much seed power, then that system is not really saturated. So you have a high gain here. So if you put like half a watt in, then you have a gain factor of what is it? 60 maybe almost. At higher powers it's less, so it's getting saturated here, but one ends up with an output power of about 35 watts for 2 watt NPRO. And the part that's new for advanced LIGO, that's this, oopsie, that's this, this high power oscillator stage. I'm gonna show you a picture of that thing. So this thing actually acts also as a laser alone. It consists of 4 of these things, what we call pump heads. So there are 4 crystals inside. And it's also built in a ring configuration. So OC stands for output coupler. This stands for shutter. And then the beam goes around here and also the other way. So if you just turn that thing on, then it will lace. It's not a concept of an amplifier. And there are actually 2 beams coming out. So we don't have this non-planar thing or so in this case. So one beam is coupled out here, and the other one is traveling all the way back, and then back to the amplifier, which would be a pretty bad thing if we won't have this high-power Faraday isolator. So I'm going to show you how that works in a minute. But that's a component that one really, really wants, because the output power of that thing here is about 180 watts. And if you say, okay, 90 watts are going this way, and then we have an amplifier here, which amplifies this 90 watts to even more, and then we send that back to an NPRO, that would be really a disaster. So we really need this high-power Faraday isolator here. Well, I'm going to come to that when I talk about the longitudinal mode selection. Actually, in the end, it kind of works like an amplifier. It's just like you need to conceptually build it as a laser, because you need the same beam sizes inside that, such that you can sort of mode match the MOPA beam to the beam which is traveling around that thing. So that's the key thing. But yeah, it's a good point.
Is there a design that one can avoid that type of isolator at the end?
I don't think so. I mean, you can try to build just an amplifier like the one we had, but neodymium vanadate is rather bad there, because for high powers, it has a low fracture limit, it has some bad thermal properties, so you can't get rid of the heat actually, and also you can't really grow big crystals for neodymium vanadate, so you want to use something like neodymium YAG. And there the absorption is lower, so you want to have something that you actually want to have a cavity to get the high power in the end. Okay, here's a schematic of the high power Faraday isolator, and it's a very special one because it's designed for powers above 100 watts. It consists of a 67-degree quartz rotator between 2 22.5 TGG crystals. I think TGG stands for terbium gallium garnet or so, some sort of garnet. And it works a way that in one way you have to subtract these 42 times 22.5 degrees, so 45 degrees. And the other way you have to add it. So you end up with a rotation of 22 degrees in one direction and 112 degrees in the other direction. So that doesn't help so much. And that's actually why you have this half wave plate here, which adds another 68 degrees. So you end up with a rotation in that direction, which is 180 degrees. So you basically do nothing except flipping the polarization by 180 degrees. On the way back, you end up with 90 degrees. And that means that you can easily block that light which is traveling back here. So here's the thin film polarizer. And if you have S polarization coming from the amplifier, you can send it through, you turn it by 180 degrees, and then you can send it through this other thin film polarizer, and then that goes to the oscillator. On the way back, you rotate by 90 degrees, and that means that that light is reflected here, and then it goes to a power meter and can be monitored in principle. Another special thing is that you also have a DKDP crystal in that setup, which is sitting here in this mount actually. And that crystal has a negative thermal lens, so it's cut in a thickness such that the thermal lens, which might be created in the quartz rotator here, is compensated such that you don't have any bad effects from the light which goes through here, except some minor kind of absorption, of course. With that setup, we observe a suppression of, or an isolation of 35 dB. So that's a normal thing which we use for LIGO. The people who invented that thing have published a paper where they showed a bit more than 40 dBs, but that's really tricky. I think they probably worked on it for like half a year or so until they got this suppression. That's a really... Pardon? Yes, yes. It's the trick is that it uses the Faraday effect to rotate the polarization of the light. Yeah. There's a huge magnetic field. Actually, you don't want to come too close with a screwdriver to that thing if you bolt it on the table, because all the screws and tools or so are really flying into this aperture here and then destroy that thing. So that's a bit tricky to handle that. So it's a huge magnetic field. Yeah. Yes. Oh yeah. The first thing we do is the light from the amplifier. So what we want to have in the laser and also in the interferometer in the end is S polarized light. What the amplifier gives you is P polarized light. So the first thing you want to do is you want to rotate it. So here's a half wave plate which ensures that the input polarization is correct. And then you have this set of a half wave plate which has to be set to this 68 degrees and so on. But then there are a couple of, actually all of these components are tunable. So the DKDP crystal, for example, can be tilted such that everything is optimal. We were told when we bought this thing the first time and we couldn't get this 40 dB suppression here, that this half wave plate does not only have to be rotated, also has to be tilted. So there's a special mount that tilts this half wave plate to make the thickness of that plate such that it really works out well. And of course also the thin film polarizers, and there's also a calcet plate in this mount here that also has to be properly aligned. So it's a rather complicated process, and we actually don't do it in that direction here, but we send light from here and then align for the maximum suppression. Actually, I took that picture here from our construction manual where the description is on how to align that thing, and that's why this light is coming from here, although it's actually in the picture I've shown before, the light comes from the amplifier and then goes to the oscillator. No. So, I mean, you want to make sure that you go kind of central through it in the middle, but there's not really any option to align that thing. So then there are 4 of these pump heads here, and I want to quickly go through it. So here's a picture of it. And it consists of different components. So here is where the laser light come in. So that's fiber coupled, and the end of the fibers is held by this mount. Then it's sent through a glass rod, a so-called homogenizer. And here's some diagnostic devices. And then that light is imaged through a dichroic mirror. So here again we have it like that the pump light is going through these mirrors and the laser light is reflected. So this is one of the dichroic mirrors, and it's sitting on a marker holder, which is kind of transparent for the pump light. So that material, it's not really transparent, but it's not like it's absorbing all that stuff and it's getting hot. And then it's sent into the crystal, which is sitting here in the pump chamber. So it's cooled with water directly. And yeah, as you can see, there are a lot of connections here for water. Here's, for example, a beam block for residual pump light, which might not go through if this coating is not perfect, but is then catched by this thing. Here's another beam block which catches actually fluorescence coming out of the crystal. So there are a lot of components, and I want to comment on some of them. So the pump light source itself consists of, it's a diode pumped laser, so neodymium can be pumped with 808 nanometers, as you probably know, and it's designed kind of backwards. So we know that we want to build a 200 watt laser. We have 4 crystals, so we have to extract somehow 50 watts from each laser crystal. And we have figured out in earlier experiments that the optical efficiency for the fundamental mode is about 20%. Optical to optical, like pump light to output light. So we need something like 200 watts of pump power per laser head, per crystal. And that's ensured by 7 laser diodes. So they are sitting in a diode box, as you can see here, in 2 rows. They are hooked up to a heat sink. So this copper thing here is the heat sink. There's a Peltier element between the actual diode housing and that heat sink. And then the fibers are coming out of this diode. So this is just for control, and then the power connectors are on the back of that thing. And we picked these diodes because that way we can choose 7 fibers, which can be put in such a pattern here, which is a kind of circular symmetric setup already, which is good because we have cylindrical crystals. So we want to have some circular symmetric pump setup. But if you have seven little dots of fibers and then you try to image that in a crystal, you might imagine that it's kind of hard to really get a round beam profile out of it, because you're creating so-called hotspots inside the crystal if you image that. So points where you have more gain than in other points, and you actually want to have a more or less homogeneously pumped light field. And that's why we introduced these homogenizers, which is basically a glass rod or a super-zero rod. And you bring the light in from one side, then it goes through the glass rod. This glass has a refractive index of about 1.5, and it's surrounded by air, which has a refractive index of 1. So you have total internal reflection. We have in the end, we have Teflon rings. And actually, you can see that these that there are these water connectors here. So the ends are water cooled. So it's not like the whole thing is circumvented by water, but the tips are water cooled because we had some problems with them getting hot. So we better add some device here.
Clamp it with a Teflon, you'll still lose pump light.
No, the part where we couple it in, the homogenizer is bigger than the cross of the 7 fibers. So and there's a very, very tiny gap here, so we basically don't lose anything. And the first reflection of the pump light on the barrel of that homogenizer is behind the clamping. Actually, it's somewhere inside here. And then you have on the output side face, we might get something. Yeah, we didn't really had problems with that, but yeah, that's true. And the pattern you end up with is shown actually here. So I took a CCD image of the fiber tip itself. So it's not perfect, but that's how the fibers typically look like. There's the simulation. So that's what you would image into the crystal if you won't have this homogenizer. And if you have it here, then the pattern looks a bit like that in the near field. In the far field, it's a bit a different story because you have some heliocentrical modes running around in this glass rod, so it's a bit not that homogeneously. But that's actually the pattern that you image into the crystal.
Why is it not nicer? The 7th pack.
This one?
Yeah, like that or something. Yeah, I mean, why not? Would it be better?
Oh, it would be nicer, yeah, but it's just a technical issue. So you have 7 single fibers, and then you stuff them into some kind of macro holder, or now we are using aluminum because that thing is water cooled anyway. But it's really hard to really have it like this perfect pattern as it's here. So that's just an example. So they are all a little bit different, but typically you have 1 fiber in the middle, and the other 6 are kind of arranged around this middle fiber. Yeah. So that light is then imaged into the crystal, and of course the crystal has to be capable to handle this amount of pump power here without breaking. What typically happens is that you have at least 26% of this light converted into heat. If that thing is not, it might be even more. And of course that heat produces some stresses inside that material, and so that might cause that material to break. And the damage threshold that you can find in the books is between 130 and 200 megapascal, depending on which literature you use. But so this is kind of the lowest number you can get. And to not break the crystal and to absorb a good amount of that light, you want to have low peak temperatures inside the crystal. So here are 2 curves. So this is a position along the rod axis. This is the temperature. It's a simulation. And these 2 curves are both calculated for an absorption of 97%. So 97%, and we say we want to have a dope region of about 40 millimeters here. So that means that you need a neodymium doping concentration of 0.2 atomic percent in a single pass configuration. So the light comes in here, and it creates this huge peak here because there's a lot of light available, and then that light is absorbed, so that temperature goes down here. To bring this peak a bit down here, you can just say, okay, we only want to have half of the doping concentration, and we double the length of the crystal. So that would lead to a very long crystal. In the end, it might even lead to fibers or so. And in order to not have that crystal too long, there is a trick one can use, and that is that one just uses the backside as a mirror for the pump light. So one adds an HR coating for the pump wavelength here, so the light is going back in that direction. And that's actually why this red curve here is a bit higher in the end than the blue one, but they are not that high peak temperatures anymore. And that actually helps a lot to not destroy the crystals, and also to bring the thermal effects a bit down. So these crystals are sitting in a pump chamber, water cooled. They are also clamped with Teflon O-rings. And the setup goes like the water. So the pump light is actually coming from this side here, and the water is coming from that side. And as you can see, the water stream coming in here does not directly hit the crystal, because we made some bad experiences in terms of noise with that. So if you just hit the crystal with some water, you can easily imagine that it starts shaking. So we have this kind of pre-chamber here, and then the water goes along here. And if you look carefully, then you can see that this shape here is a bit conical, so the water adds some speed, so it's fastest where the pump light comes in, and that leads to a rather homogeneously temperature distribution. So here's the simulation of how the temperature might look like on the barrel of the crystal, and it's more or less homogeneously, not perfect. So, and that's how that thing looks like. So that's a crystal, and then it's sitting in that chamber here, and actually, that's the actual design. So the water is coming from the top and also going through the top. It's kind of an old design. Earlier, we had the water coming in from the sides, which is a bit easier to manufacture, but it's a bit bad to mount the crystals in that whole setup then. Another component which you might have seen in this setup is the so-called long-range actuator. I've shown you this picture in the beginning, and you might have seen that it's a rather huge thing. So this base plate is about 2 meters long. Well, it's not 2, I think it's 150 or so. And we were a bit worried that that thing might expand when the room temperature changes. And actually, one can calculate that, of course. And of course, it's like if the room temperature changes by 3 Kelvin or 3 degrees Celsius, then that would cause a change in the resonator length of 54 micrometers. And for a resonator length of about 2 meters, that already matters. So you need some device to compensate for that. And that's why there is a DC stage here, a little motor, which actually moves one of the mirrors back and forth in 100 nanometer steps. So the mirror is sitting on a mirror mount, and the mirror mount is attached to a little motor. And that motor has a travel range of about 25 millimeters, which should be plenty because we don't expect the room temperature to go up by, I don't know, 50 degrees or so. So that helps to compensate for these fluctuations, and it also helps in the alignment, in the initial alignment of that whole thing, because then you have one thing which you can really carefully align. I mean, this is only 100 nanometer steps, and that's something that you can't really easily do with just one of these thumb screws on the mirror mounts. So the question is, how does it behave? And of course, we did a test of that. So we played a bit around with the AC in our lab. What you can see here is in black the room temperature, and in red the temperature of the laser box. And actually you can see that it's pretty much damped. It's a bit higher than the room temperature because the laser was running, and so it was heating up that box. But it's not too bad. But what you can still see is if you look at the position of this long-range actuator, then you can see the warmer the room temperature gets, the more it actually tries to compensate for that. So you see this 100 nanometer, or actually I think the step size was set a bit bigger here, but it's moving. And what we used as a trigger for a movement is a movement of the PZT mirror. So what's also attached here is a little PZT mirror, which we need later for the frequency control of that thing. So I'm going to talk about that in a couple of slides. So that's used as a trigger, and as soon as the long-range actuator moves, that mirror flips back and then moves again. What we don't see is that this causes any disturbances of the laser frequency or the output power. So that's important. One big concern that we had, that might mess up the laser performance, but it doesn't. So for that, we have this so-called relog counter, and that has been set to 0 at a certain time, and it just stays there. So just quickly, for this oscillator, we also have to ensure that the light is linearly polarized, and that's why we just add a Brewster plate. So it's a coated window here, and the S polarization just goes through, so the S polarized light can make its round trip in that device here. The P polarization is reflected on this little plate, and because we don't want to have any light beams bouncing around in that laser box, we built something like there are two tiny little mirrors on each side of this plate actually, which bring the light up and then out here, so out in this direction, and then it's kind of easy to catch it. It's kind of narrow in here, so it's a bit tricky to find a place where we can put the Brewster plate and then get rid of the spots which might come out here on top of it. So that light is either damped or partly monitored, so that gives us a good indicator on how well that laser performs, how well the polarization is there. And then finally, there is another device just on the output of that laser, and that's a so-called corona aperture. And the purpose of that is to really have some final beam shaping. So we had some problems with the beam, which is kind of round in the middle, but then we have a ring around the main beam pattern, which we cannot use in the interferometer. So we have to somehow catch that. And that's why we put in this water-cooled aperture here. So the light comes from that direction here. There's another thin film polarizer, which sort of cleans the polarization again. And then there's an aperture, which looks like that catches this ring. And the difference is shown here. So that's a picture without this aperture. Can one actually see that? There's a little ring outside that thing. So that's what we always had, and we cannot really get rid of it. And if you add that, so it looks weak, but it's a huge area actually, because it's a huge ring. So if you look at the numbers here, then you can see that the power which comes out of the laser box without that aperture is above 200 watts. If you put the aperture in, then the beam profile looks nice and round, but you're losing something like 20 to 30 watts, which is actually quite a lot, but that's how it is. I mean, that's why we had to water cool that thing. Okay, now we're going to talk about the mode selection, which is kind of the key point. Yeah.
Only laser rods are worked on Teflon only?
Yeah.
They don't relax over time and the pointing doesn't change?
No, they're really squeezed. So they are, there's a little groove in that pump chamber, and you might have seen this end caps on that. So you really put the laser crystal in, and then you squeeze the end caps on that laser, carefully, of course.
Teflon does not relax over time?
Well, it's slightly floating, but there's just no room that it can float away. So it's really sitting in that groove, and yeah, if that would be a bit too big, then it would float. Actually, we had a problem like that, and I'm gonna comment on that. I think tomorrow. Tomorrow, I'm gonna show some pictures of what happens if one makes a mistake. And
What is an alternative way of clamping it in place other than Teflon? Teflon is still not a very mechanically stable material.
well, you don't want to have it too hard, right? You could think about some aluminum wires or so. That seals, so you want to have something that seals and at the same time that doesn't absorb too much of the pump light. So rubber, for example, is kind of bad because it's getting warm. So we had some experiments going on with these black rubber O-rings, which was not a really great idea because they are also evaporating some material. So we figured out that Teflon is actually a pretty good solution for that. Yeah, works well. What? Can you say that again?
What is the role of the 67-degree quartz rotator?
The quartz rotator. So that okay. Let me go back. Oops. Let me go back to that slide, maybe. So you have this 67-degree quartz rotator, which actually works together with a magnet. And the rotation goes only one way. So if you go this way, then the 36-degree go like that. And if you go back, then it rotates the other way around. And together with these two TGG crystals, so you have to subtract or to add this number to that. So you end up with 6. Did I make a mistake in the calculation? So you end up with 67 minus 45. So that would be 22 degrees for one direction. For the back direction, you rotate the other way, so you have to add this 45 degrees. So you end up with 67 plus 45 degrees, which is 112. So 22 and 112. That doesn't really help you, so you need some other device which adds a certain amount such that that you have some sort of 90-degree rotation for one direction and either 0 or 180 or 360 or so in the other direction. And luckily, that can be done by a half-wave plate which rotates by another, what did I say, 22 plus or 90 minus 68 degrees. So that's why we need this additional half-wave plate. Is that the question? The rejection is like it's actually two things. So the main thing is a calcite plate here. So it's a birefringent material, which actually, but the beam separation for this plate is rather small. So it's really hard to, put some aperture or so in for one beam and then let the other one pass. And that's why there is a thin film polarizer. So that basically works as a kind of similar to a Brewster plate. And that means that this polarization here is reflected. So the P polarization would peek through. The S polarization is reflected. And then there is a curved mirror here. And that mirror directs that light to a power meter. So that's actually there as a protection because it's kind of hard to just have a beam dump there. And the power meters are designed for that. But it's also nice to have a readout and then see how much power is actually coming there. Other questions? Okay, so then let's go on. So the transverse mode selection, the the general trick with that is that all higher order modes, which don't have this rise round B profile, have a kind of a bigger cross section. So the trick is actually to add some device which catches beams which are larger than the beam that we really want. So luckily this TM00 mode is the smallest one, and we can just try to catch all the other ones. And one option would be to just don't give the other modes any gain, and that's actually what we are doing. So that's why this end pump configuration that we have helps. So the light goes in through the homogenizer, through the pump optics to the crystal. And that already helps with not having any gain in the outer regions of the crystal. So there are two actually mechanisms how you can get that. So it's called either mode selective or mode adaptive pumping. So the red beam here is a laser mode. And then you can either do a mode adaptive pumping, which means that you more or less fit the pump light to the laser beam. But for that, you really need a high quality beam profile at the pump light. So you need a high brightness. You need like 250 watt in something that's really close to a TM00 mode, and that's really hard to get and also might cause some problems in regards of thermal issues. So what we do is this mode selective pumping, and that means that we slightly focus into the crystal, and the first spot, the first waist here, is actually very close to the end of the crystal. So that's where there's still a lot of light available. So we have the main absorption in this region, and no excitation in this region. So that already ensures that it's mainly the fundamental mode which can oscillate in that crystal. And then of course the cost of that is that the pump light is again bouncing around. So that's a similar mechanism as in the homogenizer. We also have total internal reflection here at the wall. So as I said, it's water cooled. So the index of refraction outside the crystal is something like 1.5, and neodymium itself has an index of refraction of about 1.8, 1.82 or so, I think. So that still works. And yeah, that's one mechanism. We try to get a brief control over the laser mode, but that's not the main thing. So when we started working on that, we figured out that it's still a multi-mode beam coming out of the laser. So we try to add some apertures and catch away these higher order modes. Of course, that works, but if one has something like 150 watt lasers and then one adds an aperture with a size that's picked such that only the fundamental mode can oscillate in that thing, then one catches about 80% of the light. So the output power is really, really, really small, and it's kind of a rough method. So it's really like, yeah, not the smartest idea one can have. It's a simple approach, does not really work that well. So we don't have any water-cooled apertures apart from the corona aperture in the oscillator. So that's really not a good idea. So what we do instead is we do a matching of the resonator geometry, and I want to go briefly through that, and I want to use a kind of simpler test bed to explain that. So as I pointed out, we have this 4-head ring resonator. And just the thing, how we started to develop that thing was actually a 2-head test system. And if you want to really investigate some things that are going on in this rather complicated system, you can always go back to this configuration, because we figured out that if you know how to choose the resonator configuration itself, if you use the same crystals, if you use the same pump light configuration, and you use only half of the crystals, so you use only 2 instead of 4, then you would end up with about the same laser properties except the output power. So you only get an output power of about 80 watts for this setup, 160 for that, plus 35 from the amplifier, which would give you then a 200 watt laser. So I'm going to show you the effects on this simplified system here. And the phenomenology that you can observe is that you really want to have an asymmetric resonator design. So you might have realized that the arm length in this thing and also in the 4-head ring resonator are not really the same. So it's an asymmetric thing. And what happens if you build something like that is that you play around with the stability range of the resonator. And what I mean by that is actually shown in this picture here. So here's the pump power per crystal. And what's plotted here is a mode radius inside the crystals. And we actually use that as a stability criterion for the laser. So if for example, the beam radius inside the crystal becomes infinite, or if it becomes even bigger than the crystal aperture itself, then that beam can't oscillate in the oscillator, so you won't see any laser output. So now what happens if you build if you build a symmetrical resonator with two arm lengths of the same length, and you end up with this blue curve here. So that's a solid blue curve. You add some pump power, and that system is basically always stable. Now, if you change one of the arm lengths, this one, for example, and you can see that the longer the arm length is, the bigger the mode inside the crystal gets. So you end up with these solid lines. So the mode is getting bigger. And also the stability range here splits in the middle. So somewhere in the middle, the beam radius becomes infinite. And so that system is not stable at these regions here. So that's the solid lines here in different colors. And then these different patterns here show you what happens if now that you have an asymmetric resonator with a long arm and a short arm, what happens if you play around with a short arm. And that basically influences this second stability pot here. It moves it around, and it allows you to pick a certain pump power where that system operates, so where it can oscillate and where it's not really stable. What you can see furthermore, and I'm going to comment on that in the lecture on thermo-optical effects, is that the higher order modes observe a different stability range. So they are sort of bigger, and the thermal lens inside the crystal is aberrated, so they really see a different thermal lens. And that means that you need, in this case, more pump power to actually bring them to the second stability pot. As I said, I'm going to comment on that in another lecture, but the key point is that you end up with a certain region where only the fundamental mode is stable. So here, in this marked area, you have a region where the fundamental mode is stable, which is this black curve here. All the other modes are not stable yet. And that's picked as the operation point for these kind of systems. And of course, we proved that it works. So if we, these curves here are basically the same simulation as what I've shown before. But what's also plotted here is the output power of the laser with respect to the pump power. So what you can see is that the laser turns on in the first stability range. Of course, the power is not very high because you have only like 60 watts of pump power. Then that whole system becomes not stable, so the laser power goes down. And then it goes on again, and right in the beginning of the second stability range, you get a nice round TM00 beam profile. And that's actually the trick on how that is ensured. Yeah. So now I'm going to talk a bit about longitudinal mode selection. Do we have a couple of minutes more? Or? Okay. Okay. So we have several options to do that. One is, for example, to make the resonator length rather small. So I commented on that earlier, that if you have a small resonator length, then there might be only one mode that fits into the gain spectrum. And that's how the Entro works, actually. It doesn't work with the high-power oscillator, though, because, I mean, you have 4 crystals, and you need, for some other purposes, some space, so you can't make that. So the resonator length for the high-power oscillator is about 2 meters, and you have plenty of modes fitting into that. Another option would be to introduce frequency-dependent losses, for example, by an athelon. So that's basically a thin glass slide which works as a cavity, and it's so and of course you have a certain transmission condition, which is like you want to have multiples of the half wavelength should be the thickness of that slice, and if you tilt it a little bit, then you change the effective thickness, and that ensures that a certain mode fits into this cavity. And all the other modes are just, all the other frequencies are basically reflected. So that's what people do sometimes, that they add an ethalon and then they move it around either with a thumb screw or a little motor. Another option is used in these sort of DFB diodes, and that's the support of a certain mode by optical feedback. And what that means is if you have, for example, a diode laser, a laser diode, and you have a mirror on one side and a grating on the other side, then what the grating does, it creates some diffraction pattern. So the light is split, it's refracted. And only the light which is directly sent back to the laser diode is then part of the resonator. So this grating kind of acts like one of the end mirrors. And that's one option how one can narrow the frequency down for yeah, actually I've only seen that for diode lasers. I'm not sure if it also works for high power solid state lasers. So we are not doing that either. What we are doing is a technique which is called injection locking. And injection locking is a principle where actually a single frequency master laser is coupled to a slave laser or a slave oscillator in this case. So in our case, a master laser is the NPRO or the amplified NPRO because it already has a well as I said, single frequency is relative, but it has only a line width of a kilohertz or so. And that's coupled to the laser by, or the high power oscillator by a technique called injection locking. And there's some rumor going on about a story by Christian Huygens who investigated that first, and that story actually says that he was sometimes sick, laying in his bed, and there was a pendulum clock on the wall, and then he put another pendulum clock right next to it. And what he observed then is that if the frequencies of these two pendulums are kind of close to each other, then they would couple such that the frequency is eventually then the same after a certain while. So I don't know if that specific story is true, but I think it actually meets the point. So yeah, I mean, this drawing might be a bit bad because you always need a master and a slave, and these two watches are kind of the same. So maybe I should have made one a bit smaller and the other one a bit bigger, but that's a principle on how it works. So for lasers, it's like the electromagnetic field of a single frequency master laser is coupled to a slave oscillator, as I pointed out. And to do that properly, one needs to mode match the beam waves of the two lasers to each other. So one really wants to overlap the two beams. And since there is a round TM00 beam coming out of the master oscillator, we also need to build this high power oscillator such that it also already emits something like a TM00 beam by itself, because otherwise this mode matching could just not be done. And then the resonance frequency of the slave, so in this case of this oscillator, needs to be altered. So the length of that resonator needs to be changed. And that's actually the task of this little piezo element with this mirror glued on, which is sitting on this long-range actuator, which I've shown earlier. So that's a device which slightly changes the resonator length and therefore changes the resonance frequency of that laser itself. So the stability of this locking depends mainly on the quality of the resonator. So it's given by this formula, and the quality is standing at the bottom, which is good for us because this high power oscillator has an outcoupling mirror of 50%, I think, 50 or 55 or so. So the quality is rather bad. The finesse of that thing is rather bad. And that helps in terms of the locking bandwidth. So the range, so the locking bandwidth sort of tells you how close the resonance frequency of that laser needs to be to the master frequency. And then it also depends, of course, on the frequency, and then of the powers of the free running of the master laser, PM, and of the slave oscillator. And I think I've shown that on one of the slides. The power of the free running slave is about 160 watts, depending a bit on the pump power. And yeah, actually that number is going here into this formula under a square root. So now what happens if you try to couple these two systems? So what happens if you're far away from, if you're with the master frequency far away from the resonance frequency of the oscillator? What happens then is you send the master light in, and of course it's running around here and it's a bit amplified, but it's not amplified very well, because all amplification is what you get if you're right at the resonance frequency here of that system. So there's no free running field of the oscillator anymore, and it basically just operates as a saturated amplifier for the master beam. So there's no light coming back, and at that point you won't need the high power Faraday oscillator anymore, because there's absolutely no light going in that direction. Of course, you don't really want to get rid of it, because that system is not all the time locked, and you need some time for, and of course it's not perfect in reality, but if you just look at the physics, then you would realize that there's actually no light going out in that direction, and you have a lot of light coming out here. I might point out, or I might say something about this green curve here. So this green curve here would occur if you won't adapt the outcoupling degree of the output coupler for that, so that slightly changes for this amplifier configuration compared to the oscillator operation. In fact, it doesn't really matter. So I've never seen any effect. For that system, it doesn't really matter whether the outcoupling degree of this mirror is 50% or 55, maybe even 60 or so. But theoretically, it makes a little difference. Yes. So that's a locking bandwidth. So the locking bandwidth is actually this region. Yeah, I couldn't find the square root sign. I didn't use it.
It is 2 omega 0 by q
Yeah.
multiplied by that factor, or that comes in the.
It's multiplied by the square root of the.
Q is multiplied by that.
No, this whole thing is multiplied by that. So there's no brackets missing actually. Of course, you don't want to have some graduate student or so which all the time moves this piezo mirror and tries to optimize that thing. So you want to have some sort of automated scheme. And that scheme is not only used for this kind of laser stabilization, it's also used if you try to lock a cavity to some laser, a passive cavity, or even if you want to lock a laser to a gas cell or so. So it's a pretty common scheme, and it's called Pound-Drever-Hall locking scheme. And I want to try to briefly explain what's going on. So I think most of you might already have heard a bit about it. But the way it works is you have this master laser, or the MOPAR in our case. And if you look at the frequency spectrum, then you would see only one peak coming out of that laser. So now the first thing you want to do with that laser is you want to send it through an electro-optic modulator, a phase modulator, an EOM. And that is driven by a certain frequency, which is given by some sort of local oscillator here. And what that thing does in the frequency picture is it adds sidebands. So it adds an upper and a lower sideband at a distance of exactly this driving frequency. And these two sidebands are phase shifted by pi. So in other words, I have an opposing sign here. And then this phase modulated light is sent to the slave system. And of course, you want to pick the driving frequency here such that it's wider than the line width of that system, and that it's a bit narrower than the free spectral range. And the purpose of that is that the sidebands are actually reflected at that mirror here, so they don't fit in. And the carrier, this main peak here, is, well, for that it depends on where that piezo mirror stands here. So if you're right on resonance with that thing, then the carrier goes into that cavity. If you're slightly off, then part of the carrier light is sent into this oscillator, and the part is reflected. And now what's happening with the reflected part here is the sidebands and also the part of the carrier which is directly reflected at the output coupler doesn't see any phase shift. But the light which is fitting into the resonator here, that sees a phase shift actually, which is dependent on the resonator length. So if you're right on resonance, then the phase shift between the light which is going around in this oscillator and the light which is directly refracted is exactly pi. So you end up with some destructive interference, which means that all the carrier light fits into the cavity here. And then you have a photo detector which is resonant at the driving frequency of this local oscillator here. And you look at the beat signal for the sidebands. And since they have an opposing sign, the beat signal between the sidebands just cancels out. And if you're right on resonance and you have this this carrier really fitting into the cavity, then yeah, you basically see nothing at that signal. If it doesn't fit, then you end up with a signal here, because this canceling condition here is no longer given, because part of the carrier is coming out of the cavity. So in other words, what you see at this photodetector is an amplitude which is proportional to the frequency mismatch between the reference laser and the resonance frequency of that cavity here. So that beat signal is then demodulated, so it's sent to a mixer on one channel. On the other channel, you have a phase shifted signal of that local oscillator here. And what happens if these if the two frequencies are the same is that this mixer actually works as a phase detector. So you end up with an output signal which has an amplitude which is proportional to the phase shift of that system here. So that then needs to be low pass filtered. So the signal you want to get out is a DC signal, or actually I should better say you want to get rid of the high oscillating parts which you get from this multiplication of the two systems here. But what you end up with is an error signal, and that error signal needs to be asymmetric. So I think you might now argue, okay, why don't you just look at the signal, you forget about this phase modulation and you just look at the back reflected signal, and if you see that all the light goes into that thing here, then you know that you are there. And the reason why people don't do that is that that would be a symmetric signal, so you don't know if you're slightly off resonance, if you're left or right of the resonance, or in which direction you have to shift the frequency. So you want to end up with an asymmetric signal. And that signal looks like that. So what you see in the middle here is that's the signal coming from the carrier. It's aligned good. So this point here in the middle would actually be the point where you want to have the laser, and these are the two sidebands. Typical Pound-Drever-Hall signal looks a bit different. So in a typical case, you have a much higher carrier and smaller sidebands. So the fact why it looks like this for this specific system is that there's also some gain involved in that oscillator and so on. So it's a bit more complicated in this case. But in general, if you have this Pound-Drever-Hall locking scheme, you end up with a flank somewhere at the carrier, and then the two signals from the sidebands, where the flank kind of goes in the other way around. So these are some signals at different modulation frequencies. So for LIGO, we use, in this case, for the injection locking of the laser, we use 35 megahertz at the moment. If you use frequencies which are too high, then the sidebands of the next signal actually would move in here, as you can see here. In any case, you want to pick a frequency which is higher than the locking bandwidth, because otherwise the sidebands would appear somewhere here where the carrier is and where you actually don't want them. So you really are interested in that part here. And then this part here can be used as a feedback signal for the piezo in this case, but in general for some sort of reactor. I think there will be a lecture about control loops and feedback systems and so on. But that's actually the system the flank you want to use then. Okay, that's it. So I told you a bit on how that system is set up with the NPRO and the front end and the high power oscillator. I've shown you how we get the transverse mode control via this asymmetric resonator design with this certain region where that system oscillates only in the fundamental mode. And I tried to explain a bit the injection locking, which ensures that we really make this oscillator such that it has the same line width as the NPRO in the end. And that's it. So I think I took a bit more time than I was allowed to. I'm sorry for that. I don't have a watch, that's my excuse. Questions? Do you want the lecture notes or?